the pinnacle of physics, has brought us to its greatest paradox. What happens to you when you fall into a black hole? The equations give two different answers. Both are correct, and both are impossible. This is the breaking point. Your story. You cross the event horizon, and in just 12.8 seconds, you cease to exist. The end. Your observer's story. Those 12.8 seconds never end. For billions of years, you remain frozen on the horizon. This isn't a theory. Because the GPS in your phone corrects for the slowing of time by 38 microseconds every single day. But the real question is what this contradiction means. Could it mean that you never die alone? If you want to pull back the curtain on this mind-bending paradox, then hit the like button and subscribe. Because reality is far stranger than you can imagine. Are you ready? Let's begin. For years, we thought of black holes simply as the universe's cosmic vacuum cleaners. We imagined them as a one-way ticket, instantly and unquestionably destroying anything that fell in. The idea was simple. It was understandable. But it was only half the story, and maybe the most boring half, because science, especially in the last few decades, has presented us with a much stranger, much more mind-bending picture. We now know that the truly terrifying thing about a black hole isn't that it destroys you too quickly. The real terror is that it may not destroy you at all. This is the central paradox our documentary is built upon, which is why I'm going to ask you to hold both halves of this idea at the same time, without sacrificing one for the other. Half one. If you fall into a black hole, your body could be torn apart in less than a second, faster than it takes you to finish reading this sentence. Half two. For anyone watching you from a safe distance, hoppas, with any telescope ever built, for as long as that telescope exists, that 1 second never ends. You don't disappear. You freeze. Right there on the event horizon, and you stay frozen. Forever. These two sentences are in direct contradiction. But they are both true. They both emerge from the same equations, the same theory of gravity that Einstein gave us over a century ago. So how is this possible? How can two contradictory truths exist at the same time? To understand, we have to take these stories one by one. So let's start with the part everyone thinks they already know, with what actually happens to your body, the one with that strange name. Because scientists have given this process a name, it sounds like something out of a cartoon, but they call it Spaghettification. This is a technical term, used in real published physics papers by people with real PhDs. Stephen Hawking himself helped popularize the word in 1988. He used it in the book that introduced a whole generation to black holes, to describe an unfortunate astronaut falling feet first toward a black hole, slowly and then suddenly being stretched into a long, thin line of matter. It's a funny name for something that is not funny at all. Because as you approach that moment, the sensation you'd feel isn't one of being crushed or squeezed. It's not even like being pulled down hard by gravity. It's something else entirely. It's being pulled in two opposite directions by the same object at the same time, harder and harder, second by second, until there is no chemical bond in your body strong enough to hold you together. Your body doesn't break like a bone. It snaps, like a piece of taffy pulled hard enough from both ends. Only this pulling never stops, and it never gets weaker. As you get closer, it only gets stronger. Imagine a black hole the mass of our Sun, at about 100 kilometers away from it. The difference in gravitational pull between your head and your feet would be about 6 million times the force of gravity you feel right now where you're sitting. 6 million. What's left in the end is not a body. It's a thread, a line of matter a few atoms wide, stretching for thousands of kilometers. But what is the physics behind this brutality? The answer isn't gravity itself. It's the difference in gravity. Because gravity falls off with the square of the distance. Double your distance from something. And its pull drops to 1/4. But the difference in pull between the two ends of an object, the tidal force, doesn't decrease the same way. It decreases with the cube of the distance, not the square. The cube, that one extra exponent, makes an enormous difference. It means that as you get closer to something incredibly dense, the stretching force doesn't just grow, it grows explosively. This simple formula is why the moon can move the oceans without us feeling it, while a black hole can unravel a human body in far less than a second. But this is where our intuition completely betrays us. Because if a black hole the mass of the Sun is this violent, then a black hole 1,000,000 times bigger must be infinitely worse. Right? Wrong. The actual relationship is the complete opposite. The strength of the tidal force at a black hole's event horizon doesn't increase with the size of the black hole. It decreases, and it decreases rapidly. Inversely, with the square of the mass, double the mass of a black hole, and the stretching force you'd feel at its border drops to 1/4. Increase the mass 100 times, and the event horizon becomes 10,000 times gentler. When you push the numbers far enough, you arrive at something almost unbelievable. Consider a black hole about 10 million times the mass of our Sun, modest by the standards of the monsters at the centers of galaxies. The tidal force at its event horizon drops to something close to ordinary Earth gravity. You could cross that boundary, and feel nothing at all. This means the most dangerous black holes aren't the biggest ones, but the smallest. A black hole born from just a single collapsed star, the corpse of something maybe 20 or 30 times heavier than our Sun, might have an event horizon only a few kilometers wide. And the tidal forces around something that's small and dense are so violent that spaghettification happens long before you ever reach the horizon. This was the detail that made Hollywood's most scientifically rigorous black hole possible. When Christopher Nolan made Interstellar fiction, he hired Kip Thorne to ensure the film's black hole, Gargantua, was based on real physics, for the ocean world of Miller's planet to remain in orbit without being torn apart. Gargantua had to be spinning at almost the fastest physically possible rate. Thorne did the math and found it worked. It was extreme, but not impossible. So your chance of survival depends on the size of the monster. Find one that's big enough, and it can let you in without tearing you apart. Your body would tell you the danger has passed, and your body would be right. But it would also be telling only half the story, because a body is a pretty poor instrument for measuring what's about to go wrong next. Because the moment you cross that line and feel nothing is the exact same moment that something else, something much harder to imagine, starts happening to the one thing you have even less control over than your own body, your time. Because time does not flow at the same rate for everyone. This is not a metaphor. This is a literally measured, repeatedly confirmed fact about the universe we live in. and black holes push this fact further than anything else in nature. Einstein figured this out a little over a century ago. As part of his theory of general relativity, one of its strangest predictions was that gravity doesn't just pull on objects, it pulls on time itself. The stronger the gravity, the slower a clock runs compared to an identical clock in a weaker location. This is not a speculative idea. You are carrying a device in your pocket right now that depends on this being true to work. Every GPS satellite in Earth's orbit carries an atomic clock. Up there, gravity is slightly weaker than it is down here, so those clocks run very slightly faster than identical clocks on the ground. The difference is small, a matter of a few dozen microseconds per day. But if engineers didn't correct for it every single day, GPS locations would drift by kilometers. The blue dot on your phone would be off the actual road within hours. The effect is that real, not a thought experiment trapped on a blackboard. It's a correction factor sitting silently inside the navigation software in your car. This idea was even confirmed in a lab decades before GPS satellites. In 1959, two physicists at Harvard, Robert Pound and Rebka, climbed to the top of a 22.5-meter tower and measured the tiny shift in light coming down to the bottom, where gravity was infinitesimally stronger. They detected the difference. It was tiny, a few parts in a quadrillion, but it was there. But what happens when you take this tiny effect and turn the knob all the way up? At the event horizon of a black hole, the math says something almost absurd. The slowing of time doesn't stay small. It doesn't stay manageable. It goes to infinity. Stop on that word for a moment. Infinity. From the perspective of a distant observer, watching someone fall toward that boundary. That person's clock doesn't just slow down a little as they approach. It approaches a complete stop. Not metaphorically slow, but mathematically. Literally never-ending slowness. Before physicists called these objects black holes, they had an older name, frozen stars, because from the outside, a collapsing star would appear to lock up at the very brink of its own collapse and stay there forever. This is the story for anyone watching from the outside. For them, you never cross the boundary, you never disappear from view, you get fainter, you get redder, but you are there, always. But what about the person falling? What would their own experience be? By every account we have, falling in feels almost disappointingly ordinary, at least for a big enough black hole. You don't feel yourself slowing down. You don't feel time stretching. On your own clock, what physicists call proper time. The only clock that really matters for your own lived experience. You cross the boundary in a perfectly normal, finite amount of time and keep on falling. You'd look at your watch. It would say what it always says. 1 second would follow the next, just like it always has. So, these are the two different stories, both for the same moment, and neither is a lie. How can that be? How can two clearly contradictory narratives be true at the same time? The answer depends on whose clock you are reading, and on the fact that there is no one who can ever put the two accounts side by side and compare them. The person falling can't send a message back out after they cross the line saying, "I made it," and the person watching can't receive a signal confirming the crossing was complete. The two narratives are never reconciled by anyone, so they are both perfectly valid from their own point of view. NASA's Goddard Space Flight Center released a real simulation of this in 2024. They used one of the agency's most powerful supercomputers, generating 10 terabytes of data. In that simulation, a falling traveler crosses the horizon and is torn apart before reaching the central singularity just 12.8 seconds later. 12.8 seconds. That is the faller's story. But there is the other half from that same simulation. If that traveler, instead of falling in, had passed close to the event horizon, made a 6-hour round trip, and then returned to a mothership waiting at a safe distance, they would have returned 36 minutes younger than the crew left behind. 36 minutes from a 6-hour trip, even without crossing the point of no return. The effect is that real. Everything we've discussed so far is a theoretical world born from Einstein's equations a century ago. The stretching, the freezing, the two conflicting perceptions of time. These are elegant on paper. They are mathematically consistent. But now we have to ask the question, do we have any proof that they are real? What is it that takes these ideas off a blackboard, Shok-Chi, and into the real universe? Because, to prove these incredible ideas, we had to turn our telescopes to the most violent moments in the universe. And what we found. But what if this wasn't all a thought experiment? What if we've caught this cosmic horror we've told you about? This moment of spaghettification, not in a lab, not in a simulation, but in the real universe, with real telescopes. Because we have watched it, we have witnessed the moment a star is captured and torn apart by a black hole. Astronomers call it a tidal disruption event. And since the 1990s, around 100 of them have been detected, mostly by accident. A sudden flash of light from a galaxy that appeared completely ordinary days before. This rarity explains why every new discovery makes headlines. We've documented about 100 in total. After 30 years of dedicated searching, these events show not how a star dies, but how it is eaten. Because a normal supernova explodes and then cools. Its light shifts to the red end of the spectrum within weeks. But a tidal disruption event does the opposite. It stays hot, it stays blue. Sometimes for months, sometimes for years. Its color barely changes, because the black hole isn't done feeding. It's a fire that refuses to cool. This one stubborn detail is often the first clue that what astronomers are looking at is not a dying star. And in just the last 2 years, we have caught several of these in extraordinary, almost forensic detail. The theories are over. The real evidence is beginning. And that evidence was much weirder than we expected. In May of 2025, astronomers using the Hubble Space Telescope and NASA's Chandra X-ray Observatory announced something called a T2024 TVD. It wasn't where it was supposed to be. It wasn't at the very center of a galaxy, where supermassive black holes are supposed to live. It was offset, about 26 light-years from the galactic core. This was impossible. This was the unmistakable signature of a second, rogue black hole, tearing apart a star that had wandered too close. Black holes were supposed to be fixtures of their galaxies. But this was a monster, off its chain, hunting. But that was just the beginning. A few months later, astronomers reported something even more violent. A T2024 WPP, a black hole, small by cosmic standards at only about 100 times the mass of our Sun, tore apart a massive companion star in just a few days. Just days. The blast of light released is among the brightest events of its kind ever recorded. This defied expectations. A black hole this small wasn't supposed to destroy something this big, this quickly, and this brightly. The laws of physics allowed it, Yes, but we didn't expect to see carnage on this scale. Whatever happened, happened fast, and it happened for everyone to see. Then, there's one that hit relatively close to home, using the Zwicky Transient Facility along with telescopes from the European Southern Observatory. Astronomers caught a tidal disruption event about 215 million light-years away. The closest one ever observed at the time, a star roughly the same mass as our own Sun, lost about half its mass to a black hole 1,000,000 times heavier. The other half didn't fall in. It was ejected back into space in a violent outburst, and just when we thought we had seen it all, the James Webb Space Telescope changed the game completely. Last year, scientists pointed Webb at several nearby galaxies shrouded in dust. The kind of galaxies where violent outbursts like this would normally be completely hidden, swallowed by clouds of gas. But Webb saw through it. For the first time, astronomers caught tidal disruption, events happening behind a wall of cosmic dust that had hidden them from every telescope ever made before. This meant we'd been blind. We were likely seeing only a fraction of these events, the loudest ones, the most exposed ones. But now we understand. There could be countless other monsters, hunting quietly, feeding secretly. In the dusty back alleys of the universe, the scientists behind that discovery confirmed that several of those particular black holes had not been actively feeding on anything before. They were dormant, they were quiet, and then, for a few months, they were not. All of this evidence, when put together, points to one unsettling conclusion. Spaghettification is not just an equation, it's real. Rogue black holes exist. Unexpectedly violent small black holes exist. And there are black holes hunting behind the dust, hidden from our view. These findings don't just confirm our theories, more, they make us question them. They show us just how little we know about the most destructive forces in the universe. So how do we build a new understanding from this cosmic wreckage? Because the strangest, most unexpected of these discoveries actually comes from the closest, from the heart of our own galaxy. And what we found when we looked there, was how to solve one of the universe's greatest secrets with decades of patience. By watching the dance of a star around an invisible partner, because at the center of the Milky Way, 27,000 light-years away, we suspected a monster was hiding. But suspicion isn't proof. So 2 separate teams of astronomers, one led by Andrea Ghez, the other by Reinhard Genzel, spent decades staring into that dark heart. Their target was something invisible, so they watched the stars instead. They focused on one star in particular, a star catalogued as S2. Because S2 completed a full orbit around that invisible mass in just 16 years, that's a cosmic blink. It was getting close enough, moving fast enough. So much so that its path alone, Asadsi, definitively determined the mass of what it was orbiting. Both teams, RAS independently, came to the same conclusion. What was hiding at the center was exactly 4 million times the mass of our Sun. This wasn't an estimate. This was a measurement. It won them half the Nobel Prize in Physics in 2020. But that wasn't the real shock. The real proof was when that same star, Okawas S2, allowed them to directly detect the gravitational redshift in its own light as it passed closest to the black hole. This was real proof of Einstein's theory, not from a tower in Massachusetts or a satellite in orbit, but from a real supermassive black hole. We saw time bend, but bending time is one thing. Photographing an impossibility is another. Because, by definition, a black hole cannot be seen. It swallows light. So how do you take a picture of something that emits no light? The answer? You don't. You take a picture of its shadow. In 2019, a global network of radio telescopes called the Event Horizon Telescope did just that. They created a virtual eye the size of the planet, and they pointed it at the center of a galaxy called M87 Hans 55 million light years away. There lived a monster, roughly 6.5 billion times the mass of our Sun, and the image they gave us has become one of the most iconic scientific images in human history. A perfect ring of fire, surrounding a perfect circle of darkness, a silhouette of nothingness. This shouldn't have happened. It required 8 separate observatories on different continents to be perfectly synchronized, collecting petabytes of data and combining everything into a single image. It was more like magic than engineering, but it worked. And suddenly, black holes were no longer just equations. They were a place, not a place we could go, but a place we could at least see. 3 years later, the same collaboration photographed a smaller, much closer target. The black hole at the center of our own galaxy. That was the moment we understood that these monsters weren't just out there somewhere. One of them is right here, at home. All these discoveries were mind-blowing, but they were all on a scale, an understandable scale. But then there's TON 618, the largest monster in the universe. This isn't a black hole. This is an anomaly that takes our expectations of what black holes should be and renders them meaningless. TON 618 pushes the scale to about 60 billion solar masses. 60 billion. It is so large that its shadow alone, the dark silhouette at its center, is so wide that it would take a beam of light traveling at roughly 1 billion kilometers per hour. Several weeks to cross from one side to the other. This is not a planet. It is not a star. It is an object that could eat an entire solar system for breakfast. This shouldn't exist. Our models struggle to explain how something could grow this big. This quickly, in the early universe. It's an outlier, a data point that breaks the curve. It shows us that black holes can't just be big. They can be big on a scale that defies imagination. We've found rogue hunters. We've found unexpectedly savage little killers. We've found a time-bending monster in our own backyard. And then, we found a monster that dwarfs them all. These aren't theories. These are facts. Facts we have seen with our telescopes, searched and measured with our data. But all these discoveries, all these shocking truths, just make us ask a deeper question. How does the physics underlying all of this work? How does spaghettification go from equation to observation? How does the slowing of time leap from microseconds on a satellite watch to an eternity at an event horizon? Because the real horror of a black hole isn't in its mass or its shadow. It's in the game it plays with time, with space, and with the very fabric of reality, and the rules of that game. But where do the rules of this game come from? What is the real mechanism that underlies these incredibly bizarre effects? The stretching and the freezing. Let's slow down now, because the answer to these questions isn't found in shocking discoveries, but in the quiet, inescapable logic of mathematics. And to understand that logic, we have to rethink the most fundamental force that holds the universe together, gravity. Because that horrifying disintegration we call spaghettification, it doesn't actually come from the strength of gravity. It comes from the difference in the strength of gravity. Think about that idea for a moment. As you stand on Earth right now, the pull of gravity on your head is very, very slightly weaker than the pull of gravity on your feet, because your feet are closer to the center of the planet. Closer means stronger. It's a real difference, but it's also so small, about 700 thousandths of 1%, that you'd never notice. This is the gentle, reliable gravity we feel in our daily lives, the force that keeps planets in orbit and us on the ground. But that force itself, falls off with the square of the distance. That's a basic physics lesson. But the difference in the force of gravity between two ends of an object, what physicists call the tidal force, is a completely different beast, because it falls off with the cube of the distance. That one extra exponent, cubed, instead of squared, makes all the difference in the universe. Think of it like stretching a rubber band. The farther you pull the rubber band, the more it stretches. Now imagine that tidal force is a cosmic hand, pulling that rubber band harder and harder, second by second, until it snaps. Suppose you fall feet first toward a black hole, the mass of our sun, hundreds of kilometers away. You'd feel a slight stretch at first, uncomfortable, but perhaps bearable. But at about 100 kilometers away, the difference in gravity between your head and your feet reaches a force of about 6 million Gs. That's 6 million times normal Earth gravity. This isn't a crushing force. It's a force pulling every single atom of you in two opposite directions at once. No chemical bond, no atomic structure can withstand it. Your body dissolves, like a strand of spaghetti. This is why you can take the equations for gravity that Isaac Newton wrote 300 years ago. And if you push them just a little further, you get almost all the way there, without even needing Einstein's full terrifying machine of general relativity. But the strangest part of this mechanism is how it works completely counter to our intuition. Because logic would say that the bigger the black hole, the bigger the danger. But physics says the exact opposite. The tidal force at a black hole's event horizon, the point of no return, doesn't get stronger as its mass increases. It gets weaker, and it gets weaker inversely with the square of the mass, because a black hole's event horizon, its physical size, grows in direct proportion to its mass. Double the mass, and the radius doubles. But the stretching force at the boundary decreases so fast that the increasing size completely overwhelms the increasing danger. The horizon expands faster than the threat. It outruns it. This means, for a black hole of about 10 million solar masses, the tidal force at the event horizon drops to the same gentle Earth gravity that's holding your coffee cup on the table right now. You could cross that boundary and feel nothing at all. The deadliest black holes aren't the biggest but the smallest. A black hole born from the collapse of a star, just a few dozen solar masses, is so small and so dense that the tidal forces around it would tear you apart thousands of kilometers before you even reach the horizon. You wouldn't even have the dignity of crossing the boundary. Size, paradoxically, is mercy. Now that was about your body, but what about your time? What's the mechanism at work there? Because the slowing of time isn't a light delay, an optical illusion. It's a real warp in the geometry of space-time itself. Einstein's key insight was that gravity and acceleration are fundamentally the same thing. Standing on the surface of a massive planet feels like you are being pushed down. Sitting inside a windowless rocket that's accelerating upward in empty space would give you the exact same feeling of being pushed. Physicists already knew how acceleration affects clocks. Einstein's genius was realizing that if acceleration does it, then gravity must do it too, because it's functionally the same thing. different clocks sitting in different amounts of gravity. Stop agreeing on how much time has passed. Black holes just take this effect and turn it to infinity. In the equation that determines how much a clock slows down at the event horizon of a black hole, sit at a certain point, yet the denominator goes to 0, and dividing by 0 in math means infinity. This means that, for a distant observer, the final moment of a falling object never ends. This is why physicists originally called these objects frozen stars, because a collapsing star from the outside would appear to do exactly that. It would freeze, and it would stay frozen forever. For the person falling, time flows normally, but for everyone watching them, that moment never ends. So how can these two contradictory realities coexist? How does this not create a logical failure? Because this is the universe's most brilliant trick. There is not a single observer who can ever confirm both stories at the same time. Alice, the person falling, can't climb back out and compare notes. Bob, the person watching, can't get a complete report from the other side of the horizon. The two narratives are forever insulated from one another. Nature has built just enough lag into the system to keep its story consistent. And this isn't just a word game. This is built into the equations that describe the spacetime around the black hole, the way light propagates, the way signals are sent. It is all bent to preserve this separation. This is why, at a deeper level, all of these mechanisms point to one thing: that reality at the edge of a black hole. And that reality takes on a completely different shape depending on who is asking. This is why there's a mechanism to support the strangest idea in this entire documentary. The idea that nothing that falls into a black hole ever actually finishes falling. It's called black hole complementarity, and it was developed in the early 1990s, largely by Leonard Susskind. This idea isn't a clever trick invented to solve a riddle. It's a consequence of taking Einstein's equivalence principle to its final logical conclusion. Remember, free fall is, locally, indistinguishable from floating in empty space with no gravity at all. Susskind's argument was that this principle has to be applied consistently, all the way to the event horizon. This means, for an outside observer, Bob, anything falling in never quite reaches the event horizon. Instead, it gets smeared onto something called the stretched horizon. This is a hot, turbulent membrane that sits a hair's breadth above the mathematical boundary. From Bob's perspective, all the information of what fell in, holds, gets spread across the surface, like ink soaking into paper. This isn't a metaphor. This is a serious physical statement. Building on foundations laid in the 1980s by Kip Thorne and his colleagues with the membrane paradigm, they showed that for any calculation from the outside, you can treat a black hole's event horizon as if it were a real physical surface, with electrical resistance, masses, with viscosity. But for the person falling, Alice, there is no such thing as a stretched horizon. She passes through the boundary smoothly, in a finite amount of time, and feels nothing out of the ordinary. So, which is it? Is there a wall or not? The principle of complementarity says both, at the same time. And this is allowed, because Alice and Bob can never compare notes. By the time Alice is in a position to send a signal to Bob saying, "Hey, there's no wall here," she has already passed the point from which no signal can ever reach Bob. The geometry of the universe has been bent in just the right way to prevent these two contradictory stories from ever coming into direct confrontation. This idea connects to something even bigger, called the holographic principle. This is one of the strangest ideas to come out of physics in the last 50 years. In the 1970s, Jacob Bekenstein discovered that the maximum amount of information a black hole can contain depends not on its volume, but on its surface area. This is contrary to every other object we know. The information capacity of a book depends on the volume of its pages. A hard drive's capacity on its physical volume. But black holes don't follow this rule. They act as if everything that falls in is recorded on the boundary, rather than packed into the interior. This is expressed mathematically in the Bekenstein-Hawking formula, which states that the entropy of a black hole, its information content, is equal to 1/4 of its event horizon's surface area. The area, not the volume, just the outer shell. Susskind and Gerard et Hooft took this idea even further. Maybe this isn't just true for black holes. Maybe it's true for the entire universe. Maybe everything that happens in three-dimensional space can in principle be completely described by information living on a two-dimensional surface somewhere on the edge of everything. It's like a hologram, where a two-dimensional surface contains a three-dimensional image. This idea was given a concrete footing in 1997 by Juan Maldacena, who found an exact mathematical equivalence between a theory of gravity in a curved space and a completely different theory living on the boundary of that space, with no gravity in it at all. It is one of the most cited results in modern theoretical physics, but there is a problem with this elegant picture, a crack, because all of these mechanisms are based on the assumption that falling into a black hole is a smooth, gentle experience. But what if it's not? In 2012, 4 physicists known as AMPES published a paper that shook this idea to its core. They argued that modern black hole physics rests on 3 fundamental assumptions that almost every physicist would individually agree to. 1. Information is never truly lost. 2. Sagias, the principle of complementarity holds Gauya, and it's a gentle crossing for the falling person. 3. Physics outside the horizon behaves as quantum field theory says it should. MPS did the math carefully and found something disturbing. You cannot hold all 3 of those assumptions at the same time. At least one of them has to break. And if the one you have to give up is the gentle crossing story, what do you get? Something truly horrific. Instead of a smooth, ordinary passage, the falling person slams into a wall of extraordinarily high-energy particles at the boundary. Physicists literally started calling this a firewall. Not symbolically, not poetically. A firewall made of real particles, with enough energy to instantly incinerate anything that touches it. This would mean that everything we told you a few minutes ago, the frozen library, the wall of photographs, the gentle infinite stillness, might just be wrong. Utterly wrong. It would mean that instead of a peaceful transition, it would be like stepping directly into the exhaust of a rocket engine. This debate has raged for over a decade. Nobody has solved it. Not Susskind. Not Hawking before he died. Not anyone since. So, there are 2 live possibilities in physics right now. 1 is that the edge of a black hole is a quiet, eternal library, holding a frozen record of everything that has come before. The other is that the experience of arriving at that edge is not gentle, but an instantaneous, violent annihilation. All these technical details, all these equations and paradoxes, bring us to the brink of one final question. What does it all mean when you put these mechanisms together? What does it tell us about death, about time, and about our place in the universe? Because where these ideas lead is the most exciting part, and that takes us. But where does this leave us? The stretching, the freezing, the two contradictory realities, the possibility of a firewall. All of this mind-bending physics brings us to the brink of one final question. What does it really mean to fall into a black hole? It's time to put the theories aside, because now we reach the climax of this documentary. This is no longer about equations. This is the proof that you never die alone. This is the moment where we find, in the darkest heart of the universe, the most unexpected companionship. Brace yourselves, because it's about to get dizzying. And it all starts with a simple question. If, by definition, no observer in the universe can ever actually see you cross an event horizon, then, in any real sense, did you ever finish falling in? This isn't a riddle. This is a serious position argued by some of the most respected theoretical physicists alive today. And the person who argued this idea most forcefully was the Stanford physicist Leonard Susskind. His argument was simple, but its implications are staggering. From the perspective of everyone outside a black hole, and remember, outside is the only perspective any of us will ever occupy. Nothing ever actually crosses the event horizon. Everything that falls toward it gets spread out into an impossibly thin layer. Right at the boundary, frozen in place, forever approaching, but never touching. It's called the stretched horizon. But it's not just a name. It's a radical new picture of what's actually happening at the edge of a black hole. It builds on Kip Thorne's membrane paradigm, but it takes it to a much stranger place. Because if this idea is right, then the event horizon of a black hole at any given moment carries the imprint of absolutely everything that has ever fallen into it before. Layered, compressed, never fading. This means when you fall into a black hole, you are not stepping into an empty grave. In a very real, physical sense. You are joining a library, frozen in time. A place where every creature, every speck of matter, every single photon of light that has come before is still there, still present. Imagine the event horizon not as a boundary for a moment, but as a wall made of completely undeveloped photographs. Each layer of that wall is the final moment of someone or something, a star that collapsed 12 billion years ago, a spacecraft we'll lose decades from now, and eventually you, all imprinted on the same surface, in the same place, at the same time, forever. At least, that's how it is for everyone standing outside. Think of the black hole at the center of our own galaxy. About 4 million solar masses. It's been there for billions of years. In that time, it has consumed entire clouds of gas, countless asteroids and comets, and very likely, a few stars that wandered too close. According to this theory, every single one of them is still there, imprinted on the same boundary, layered on top of each other. A record that stretches back long before our own species ever existed. This is the universe's deepest secret, the idea that in the place most associated with annihilation, something close to the opposite might be true. But there's an obvious problem here. For Alice, the person falling. None of this happens. She crosses the boundary smoothly. She sees no frozen wall. She just falls into an ordinary darkness. This is where black hole complementarity comes in. both stories are true, because no one can ever check both. The geometry of the universe ensures that Alice and Bob's accounts remain forever separate. This is one of the deepest ideas in modern physics, and it leads to something even more astounding. Because this idea rests on a fundamental principle that information is never destroyed. This was at the center of the famous decades-long disagreement between Stephen Hawking and Leonard Susskind, known as the Black Hole War. Hawking argued that information was destroyed. Susskind argued it had to be preserved. And in 2004, Hawking publicly conceded that he had lost the argument. This means that information somehow survives. But how? This is where we arrive at the most epic moment of this documentary. Because this isn't just a theoretical debate. This is an experiment being run by the universe itself. And we are starting to see the results. We are learning that information doesn't just survive. It escapes. Hawking himself proved that black holes aren't completely black. They slowly evaporate through a faint leak of particles called Hawking radiation. For years, this radiation was thought to be completely random, carrying no information within it. This would mean information was lost forever, a violation of one of the most basic laws of quantum mechanics. But then, in just the last few years, between 2019 and 2021, a group of physicists led by Netta Engelhardt changed everything. Using a piece of math called the Island Formula, they showed that the radiation leaving a black hole could in fact carry the lost information back out. They had been trying for decades to match a specific shape, known as Don Page's Page Curve, which tracks how much information should be in the radiation leaving a black hole. Every simple calculation produced the wrong shape. The Island Formula was the first approach to reproduce it correctly. This was revolutionary. It meant the frozen library doesn't just sit there for as long as the black hole exists. It can, somehow, transformed, scrambled, almost unrecognizable, outlive the black hole itself, carried back into the universe on the last wisps of radiation. This means that falling into a black hole isn't an end. It's a transformation. Your body, your time, your experience ends, but the most fundamental information about your existence gets rewoven into the fabric of the universe. You are not erased, you are translated. And this brings us to the deepest, most philosophical question. If the universe, at its most fundamental mathematical level, remembers that you were here, then did you ever really leave? Because this idea redefines the words loneliness and eternity. You are no longer alone, because you are joining a library with everyone who has come before you. And you are no longer gone forever, because the information of your existence may live on as long as the universe itself. And this idea is the ultimate point of all this complicated physics, all these equations and theories, to tell us that the universe does not forget, and that is perhaps the most human, most comforting truth in this entire story, because we spend our lives quietly fearing oblivion, of disappearing without a trace, of the universe carrying on as if we were never here. But then, physics gives us this strange, technical, mathematically serious idea. And it says that in the place most associated with annihilation, something close to the opposite might be true. Not comfort, but not nothingness either. But this comforting idea is in direct conflict with the firewall paradox. Because if the falling person hits a firewall, Then the gentle crossing, the frozen library. All of it goes out the window. This is a live debate in physics right now. And in the last few years, some physicists have started to connect this paradox to an equally strange puzzle in quantum mechanics called the Wigner's friend paradox. In short, one physicist performs a measurement inside a closed lab. A second physicist outside treats the entire lab and the observer within it as a single big quantum system that hasn't been measured yet. Both descriptions are mathematically valid. Both physicists can be completely right while having completely incompatible narratives about whether a measurement has taken place. If that sounds familiar, it should. It's the same basic shape as Alice and Bob, just moved from a black hole horizon to a closed laboratory. If the connection is right, it suggests the firewall problem isn't really about black holes at all. It's about a much deeper crack in the way we think about observation and reality coming together. This brings us to the true frontier of human knowledge. We are close enough to touch something this strange, but we are not yet advanced enough to fully understand it. But this uncertainty shouldn't scare us. It should tell us that every big idea in this film, the stretching, the freezing, the layered library at the edge, the possibility of a firewall, came from taking Einstein's century-old equations seriously and pushing them to a place no one expected. No one invented this to be dramatic for a documentary. The drama was already sitting there in the math, waiting for someone patient enough to read it right. But there's one more layer to this story, because if everything is preserved in the frozen library, what if the library itself doesn't last forever? This is where Stephen Hawking comes back into the picture, because in 1974, he proved something no one expected. Black holes are not actually eternal. They slowly leak, with a faint trickle of radiation that now bears his name. Every black hole in the universe is losing mass every moment, and given enough time, will eventually evaporate completely. The process is ridiculously slow for the black holes we know. The black hole at the center of our own galaxy would need a time far longer than the current age of the universe to lose a meaningful fraction of its mass this way. But, in principle, it eventually ends. And here's the question that should really bother you. If that radiation is completely random, carrying no trace of what fell in, then everything frozen on that boundary, every layer of that library, evaporates into meaningless static. It's gone. This is the black hole information paradox, and it has remained largely unsolved for 50 years. Because it sits at the collision point of physics' two most successful theories, general relativity and quantum mechanics. But then, just a few years ago, a breakthrough. Physicists led by Netta Engelhardt, using the island formula, showed that the departing radiation could in fact carry the information back out. This means the frozen library doesn't just vanish, it is somehow released back into the universe, scrambled beyond recognition, but not erased. This means a black hole may not be an end, but a gateway, a place where information is converted from one form to another. And this brings us to a question that sounds like a conspiracy theory, but isn't. If everything that falls into a black hole is never truly lost, just converted to another form, could our own universe have started exactly that way? A handful of serious physicists have considered versions of this idea, from Lee Smolin's cosmological natural selection to Nikodem Poplawski's proposal that our universe might have been born from a white hole at the other end of a black hole inside another, larger universe. These ideas are untestable. They are unprovable, but they tell us something, that even our best equations, when pushed to their limit, whisper to us that the universe may not be an end, but an endless cycle. And this brings us, as we end this film, to the newest, strangest idea, which emerged just a few weeks ago. What if the thing we've been calling a black hole, all this documentary, doesn't actually have a real event horizon? In June of 2026, physicists named Daniel Jampolsky and Luciano Redzolla published research suggesting that a collapsing star might not always finish the job, that instead of forming a true horizon, the collapse might trigger something like a little bubble universe inside, pushed outward by dark energy, halting the collapse before it crosses that final absolute line. The result is an object called a gravastar, something that looks almost identical to a black hole from the outside, but with no true horizon and no singularity at its center. If gravastars are real, it means some of the math we've walked through before might not apply. At least not to every object in the universe. It's a reminder that science is not a finished body of knowledge. It is being actively worked on by people right now. As you are watching, every single piece of it, all these epic discoveries, all these mind-bending theories, bring us back to one place, the edge of humanity's understanding of our relationship with the universe. And now it is time to slow down and reflect, because all of this science, all of this math, is meaningless if we don't ask what it means for us. So, what does it mean for us? So what does this mean for us? All this science, all this cosmic drama, why should we care? Because the story of a black hole is not just the story of an object, it is our story. It is a reflection of our relationship with our place in the universe, with time, and with our deepest fears. Now is the time to slow down and reflect. Because in the midst of all these epic discoveries and mind-bending theories lies a fundamental truth about what makes us human. And to find that truth, we need to dive into some of the biggest contradictions we've set up throughout this film. And the first contradiction is the most obvious one, the contrast between an eternity and an instant. On one hand, you have the frozen, eternal moment at the event horizon of a black hole. For an outside observer, the last second of a falling astronaut never ends. It hangs there for billions of years, frozen like a crystal of time, forever. But on the other hand, you have the astronaut's own experience, the reality measured on her own watch, felt in her own nervous system. And that reality is an instant. For the black hole at the center of our own galaxy, it's a little over a minute. For TON 618, the largest black hole we know, it's maybe 3 days. Eternity and 3 days. Both are completely accurate descriptions of the same event. How can this be? The tragic truth of this is that the gap between the two timescales is unbridgeable. We, with our fleeting lives, exist in a 13.8 billion-year-old universe. The average human lifespan isn't even a blink of cosmic time. An observer watching that frozen astronaut could live out his life, the lives of his children, and 1,000 generations after them, seeing that final moment never end. This is a profound sadness that comes from confronting timescales beyond our comprehension. We are creatures who can contemplate eternity, but never experience it. But there is a beautiful truth to this story too, and it lies in that instant itself. Because that 1 minute, those 3 days, no matter how short, are not meaningless. They are a lived experience, a subjective reality measured by one's own clock. And this is the deepest gift the universe gives us: the ability to experience a moment. Eternity is an abstract concept for those looking from the outside, but a moment is ours, entirely ours. This is why you too live in this paradox every day. You feel time flowing both cruelly fast and sometimes forever. A minute after a great loss can feel like a lifetime. An hour in a moment of great joy can fly by like a second. You are both the frozen observer and the falling astronaut of your own life, and your ability to hold both these truths at once, what makes you human. And that brings us to the second contrast: solitude and communion. The act of falling into a black hole is the most absolute loneliness imaginable. Imagine a moment with no planets, no spacecraft, no other source of light, just you and the single point of gravity pulling you in. No reference points, nothing to measure against. Physicists and astronauts describe this moment as a silence unlike any on Earth, a moment where the universe has narrowed to a single point, and you are falling right into it. This is the pinnacle of cosmic isolation. No one can help you. No one can hear you. You are absolutely alone, but at the same time, the same laws of physics tell us the exact opposite. Because if the stretched horizon theory is right, you never fall alone. You join a queue. The queue of everyone and everything that has crossed that same threshold before you. Gas from a star that died billions of years ago. Ice from a comet. And maybe, in the future, an explorer from another planet, all come together on the same surface, in the same frozen moment. It is a tragic communion, because no book in this library can communicate with another. They are all forever isolated from each other. But it is also a profoundly beautiful communion, because it says that no one, no matter how far they fall, no matter how completely they disappear from view, is ever completely erased. A record remains. A trace remains. This is why you two live in this contradiction. As a species, Spaghettification, we are a lonely species, adrift on a pale blue dot in a 93 billion light-year-wide observable universe. The voids between galaxies are unimaginable. But at the same time, we are connected to billions of other humans on this planet, and countless generations past and future. We sometimes feel the deepest loneliness, but we are also all made of the same fundamental atoms, or the same stardust. You are both a lonely island in the cosmic ocean and part of the entire archipelago of humanity. Black holes remind us that even in the moment of most absolute isolation, there can be an unexpected community. And finally, there is a third contrast: power and understanding. The power of a black hole is absolute. It bends light. It stops time. It tears apart stars. There is no known physical force that can resist it. Compared to it, we are incredibly fragile and powerless. Our bodies cannot withstand the tidal forces of even the smallest black holes. Our technology cannot take us even to the nearest one. Physically, we are completely helpless before these monsters of the universe. This is the tragic truth of our existence. In the face of the universe's most powerful forces, we are nothing. But here is the most astonishing turn. Because while we may be physically weak, we can challenge it with our minds. We can understand it. Every single idea we have discussed in this documentary is a triumph of the human mind. We couldn't go there, we couldn't touch it, but we wrote equations. We built telescopes, and from millions, even billions of light years away, we unlocked the secrets of these objects. This is the most beautiful expression of the human spirit, the ability to reach with our minds where we cannot go physically. The Event Horizon Telescope that photographed the event horizon of a black hole is a testament to what humanity can achieve when it comes together. 8 different telescopes, hundreds of scientists, all working together to answer one impossible question. This is why you too have this power. You may not be able to stop a black hole. You may not be able to move a star, but you can understand it. You can ask questions about the universe. Learn, ye awe and wonder. This is your superpower, the power to understand. And this power is no less impressive than gravity itself, because it defines our place in the universe. We are the creatures who not only exist, but who question existence itself. These 3 contrasts, eternity and the moment, solitude and communion, power and understanding, lead us to one conclusion. Black holes are not just astronomical objects, they are mirrors, in which the universe shows us our own reflection. But there is more to see in this mirror. Because beyond these philosophical reflections, there are even stranger places these ideas lead. And they are. And these ideas lead, and that lesson is perhaps the most unexpected one. Because even though this story is about one of the most complex objects in the universe, it's fundamentally about a very human fear, the fear of the unknown. When Walter Wagner and Luis Sancho sued the US government in 2008, they were ridiculed. Their physics was wrong. Their lawsuit went nowhere. But their fear, that underlying primal anxiety, was real. And that fear reveals a deep truth about our relationship with science. This is why now we descend into the final philosophical layer of this documentary. This is no longer just about black holes. This is about what we do with knowledge, how we live with uncertainty, and what it means to be human in the face of the universe's greatest mysteries. And this brings us to the first contrast: certainty and uncertainty. Science is a quest for certain answers. We measure, we calculate, we verify. Every number, every equation in this documentary is a product of this quest. We measured the mass of the black hole at the center of the Milky Way to be 4 million solar masses. We photographed the shadow of M87 from 55 million light years away. These are moments of certainty, monuments to humanity's collective intelligence and perseverance. This knowledge gives us a foundation, a foothold. It tells us that at least some parts of the universe are understandable, whilst measurable and knowable. But that same science, inevitably, also leads us to the brink of uncertainty. The black hole information paradox has been unsolved for 50 years. The question of whether it's a firewall or a gentle crossing is still a matter of debate. Whether our universe was born from within a black hole remains an untestable speculation. This is the tragic truth of science. The more we learn, the more we realize we don't know. Every answer gives birth to 10 new questions. Our search for certainty always leads us to a deeper ocean of mystery, and this, for some, can be unsettling. Living in a universe full of unanswered questions can feel unstable. But there is a beautiful side to this, because uncertainty is where curiosity is born. If we knew everything, we would have no questions to ask. There would be no new worlds to discover. Science is not a finished book, but a story that is still being written. And each of us has the potential to add a sentence to that story. Uncertainty is not an end, but an invitation to dig deeper, to learn more, to imagine more boldly. This is why you too live your life between these two poles. You know for certain how much your salary is, where your house is, but you don't know what tomorrow will bring, what the ultimate meaning of your life is, and that uncertainty can scare you, but it is also what pushes you forward. It's what makes you try new things, take risks, love. Because the beauty of life lies not in knowing all the answers, but in continuing to ask the questions. And this leads us to a second contrast: the tension between fear and curiosity. Black holes are, by definition, scary. They challenge our most basic survival instincts. They represent annihilation. The end, the point of no return. Wagner and Sancho's fear, however scientifically unfounded, was understandable on this primal level. The idea that something could compress our planet to the size of a marble is viscerally terrifying. And that fear serves a purpose. It protects us from danger. It pushes us to be cautious, to consider the consequences. But the same object, the same terrifying idea, also triggers our deepest curiosity. Scientists like Stephen Hawking, Kip Thorne, Andrea Ghez dedicated their lives to studying these frightening objects. Instead of running from the fear, they ran towards it. Because there is a fine line between being afraid of something and being fascinated by it. And curiosity is the force that allows us to cross that line. Curiosity makes us ask, why? How? What does it mean? This is humanity's greatest driving force. It's what brought us out of caves, enabled us to cross oceans, and made us point telescopes at the stars. It is the desire to pierce the darkness of fear with the light of understanding. This is why you too, strike this balance every day. You fear the unknown. You fear starting a new job, entering a new relationship, stepping outside your comfort zone. This is natural, but you are also curious. You wonder what that new job will bring, who that new person is, what lies beyond that comfort zone. And often, curiosity wins over fear, because the human spirit is designed not to stay in the safe harbor, but to discover new horizons. Black holes remind us that fear and curiosity are two sides of the same coin, and which one we choose defines us. Finally, this brings us to the deepest contrast, the struggle between meaning-making and meaninglessness. The universe, on its own, is meaningless. It just is. It operates according to the laws of physics, neutron stars, galaxies, black holes. None of them carry any inherent meaning. 13.8 billion years of cosmic history is completely indifferent to our existence or non-existence. This is the tragic, cold truth of existence. In a vast, indifferent universe, we are just short-lived accidental events. This thought of meaninglessness can be overwhelming. But here comes the most miraculous but. The universe may be meaningless, but we are not. We are meaning-making machines. We look at this meaningless universe and see order, beauty, and purpose in it. This documentary itself is a testament to this process. We took meaningless equations and data points and turned them into a story, a meaningful narrative, art, music, love, philosophy. All of these are our attempts to impose meaning on an indifferent universe. We are the universe's way of making sense of itself. As Carl Sagan said, we are a way for the cosmos to know itself. This is why you too are searching for the meaning of your life. You don't expect to find it somewhere out there. You create it. You create meaning in your relationships, in your work, in your passions, in the questions you ask You are an artist adding color to a meaningless canvas. And this is perhaps the noblest, Chachkas, most important task of being human. Black holes remind us of the universe's indifference, but they also highlight our incredible capacity to create meaning in the face of that indifference. Certainty and uncertainty. Fear and curiosity. Meaning and meaninglessness. These tensions lie at the heart of the story of black holes, and they also lie at the heart of the human experience. But beyond all these deep thoughts, there is one final piece to complete this story, and that piece brings us back to where we started, to that courtroom in Hawaii, because the ultimate outcome of that case gives us one final vital lesson about science itself. And that lesson is perhaps the most important one. When Judge Helen Gilmore dismissed Wagner and Sancho's case, she didn't do it because she had solved the physics. She did it because she had no jurisdiction to shut down a machine that no American court controlled. But before she closed the file, she wrote something unusual for a dismissal. She noted that this highly complex discussion concerned more than just physicists. Even in dismissing the case, the judge acknowledged that the underlying issue was real. And this tells us something profound about the relationship between science and society. This leads us to one final set of contrasts, and the first is the tension between expertise and participation. Science is a highly specialized field that requires years of training, rigorous mathematics, and specific knowledge. It takes a lifetime of study to understand Kip Thorne's Nobel-winning work or Netta Engelhardt's island formula. And it is important to respect that expertise. Wagner and Sancho's mistake was to reject that expertise and trust their own flawed calculations. This is a tragic misunderstanding of the scientific process. Science is a battle of ideas. But that battle is fought according to the rules of evidence and peer review. But there is a beautiful side to this story. Because science is not just for experts, its consequences affect all of us. As Judge Gilmore noted, the safety of the Large Hadron Collider concerns all of us. Climate change, artificial intelligence, Cheek's genetic engineering. These debates cannot just be had in labs. They must be had in the public square. This is the power of participation, the right of non-experts to ask questions, to voice concerns, and to hold scientists accountable for the implications of their work. Wagner and Sancho's method was wrong, but their underlying impulse, the impulse to question the impact of science on society, is a vital part of a healthy democracy. This is why you are a part of this balance. You may not be a physicist. You may not understand the equations, but you are a citizen. You have the power to ask questions, to learn, and to make your voice heard. Science cannot exist in an ivory tower. It must exist in the world we all share. This leads us to a second contrast: the duality between creation and destruction. The Large Hadron Collider is a monument to human creativity. A 27-kilometer ring of magnets, colder than deep space, detectors the size of cathedrals, thousands of scientists, over 100 countries, all coming together to recreate the conditions of the beginning of the universe for a fraction of a second. This is an expression of humanity at its best: collaborative, curious, and in pursuit of the impossible. But that same machine, in the eyes of Wagner and Sancho, was the ultimate tool of destruction, the potential to create a black hole that could swallow the Earth. This is the tragic dilemma of technology. Our power to create always goes hand in hand with our power to destroy. We used fire both to warm ourselves and to burn. We split the atom both to generate energy and to destroy cities. Every new technology contains both of these potentials, but there is a beautiful side to this story as well. Because the story of the LHC shows us that creation is often more powerful than destruction, the machine turned on, and the world did not end. In fact, what stopped the machine in 2008 wasn't a black hole or a lawsuit. It was a bad solder joint. It's an almost comical detail, but it tells us something important. Our greatest fears are often overshadowed by our greatest achievements. The LHC has since run safely for over a decade. It discovered the Higgs boson. It deepened our understanding of the universe. And it hasn't created a single black hole. This is why you too face this balance in your life. You might be afraid to create something new, to start a business, to build a family, to make a work of art, because every act of creation contains the risk of failure, a kind of destruction. But the urge to create, usually wins, because the human spirit is programmed to build, watch, to explore, and to grow. Finally, this brings us back to where this documentary began and ends, the relationship between storytelling and reality. Wagner and Sancho told a powerful story, a story that was simple, scary, and emotionally resonant. A machine, a black hole, the end of the world. It was a modern version of the apocalyptic stories we've been telling for thousands of years, and stories are powerful. They shape the way we understand the world. But in this case, the story didn't match reality. The physics was wrong. The risks were exaggerated. This is the tragic danger of storytelling. When it becomes detached from facts, it can lead to misinformation, conspiracy theories, and unnecessary fear. But there is a beautiful side to this story too, because this documentary itself is a testament to the power of storytelling. We have told a story too, but our story is grounded in reality, in evidence, yet and in the scientific process. We took the real, verified physics of black holes and turned it into an understandable, false, and hopefully engaging narrative, because reality is no less powerful than fiction. In fact, it is often far stranger, more wonderful, and more awe-inspiring. The story of the world being compressed to the size of a marble is scary, but the story of time freezing forever at the event horizon of a black hole is far deeper, far more thought-provoking. This is why you too are the storyteller of your own life. Every day, you turn your experiences into a narrative, and you have a choice. Will you tell stories based on fear and misinformation? Or will you tell stories based on curiosity, understanding, and the complex beauty of reality? Expertise and participation, creation and destruction, storytelling and reality. These final thoughts bring this journey full circle. We now know that the story of a black hole is not just about astrophysics. It is about us. It is about our greatest achievements, our deepest fears, and our unending quest to understand our place in the universe. We have come to the end of this long journey. We started in a Hawaiian courtroom. We traveled to the edge of the universe, the end of time, and the depths of the human spirit. And now, it is time to bring all of this knowledge together. In this journey, we have studied the darkest objects in the universe, black holes. But there's something I haven't told you. What if our universe was born from just such a place? What if the Big Bang wasn't a beginning, but the end of a previous one? In our next journey, we go before the beginning of time. What was there before that first moment? Are you ready?